Okay, I'm going to start the recording. I want to do, we did talk last class about section 10.3, and you'll notice that we do have assignments now that are going to be due on Wednesday and Friday of this week. Even though you're you're doing your remedial, you're thinking about your remedial problems, but you also have to think about your homework too. Okay, so, but let me give you a moment to copy this example down. Okay, so in this problem, we want to find the equations of both the osculating plane and the normal plane of this helix at the point 0, 1, pi over 2. And then we want to find the curvature of this helix. So we actually, this problem is a problem actually from your textbook, okay, in section 10.3. It's actually example 7, but I want to just fill in some more details for you. So we know what a helix looks like, right? We know a helix, how it looks. Well, that's not actually a good picture. Let me try again here. Okay, we know what a helix looks like. All right, and of course, this helix is only since, well, yeah, we just want to find, we want to find the equations of the oscillating plane, the normal plane of the helix at a point on the helix. So let me ask you, can I, based on this point, 0, 1, pi over 2, what's t got to be? So as t varies, we trace out the space curve, and different points on the space curve correspond to different values of t. And Hyunwoo says that pi over 2 would be the value, and that's right, because the cosine of pi over 2 is 0. The sine of pi over 2 is 1. And then, well, if t is pi over 2, there's pi over 2. Okay. So what do you think the first thing we need to do for this problem is? And actually, hold that thought. I want to bring up one thing. One moment, class. I want to bring up the ebook real quick. Hold on. It's worth doing. Hold on. Just got to find it in the ebook. Okay. Okay. So here is a picture of the TNB frame. The space curve is in blue. You have a tangent vector. Okay. So there's a point on the space curve. Protruded from that point is a tangent vector to the space curve, the unit tangent vector t. And then you have a normal vector, the unit normal vector that's perpendicular to the tangent vector. And then there's a binormal vector that's perpendicular to both the tangent vector, the unit tangent vector, and the unit normal vector. And the binormal vector is a unit vector as well. So the osculating plane contains what vectors in this picture, in figure 6? The osculating plane contains what vectors? Do you remember from our last lecture? Well, osculate means to kiss, right? So the plane that kisses the space curve, as Ellie, and Ellie, you're right, the plane that kisses the space curve contains the tangent and the normal vector. Okay, now how are we going to get the unit tangent vector there in the picture? How are we going to find? All we know is we know the vector function that traces out the space curve, the helix in space. How are we going to get the tangent vector? Okay, Hunu's right. We got to find r prime of t, because we got to find r prime of t, right? Right. We got to find the derivative vector, because the derivative vector would be tangent to the space curve at that point. And then, of course, the unit tangent vector would just be the derivative vector r prime divided by the length of r prime. Okay, so let's go back now to the ditto here. Okay, so here we go. Here we go. All right, and let me just see here. Might use my stylus. On here. So let's remind ourselves that r of t, the position vector or vector function for the space curve, consists of components cosine of t, sine of t, and t. And so the derivative vector has components negative sine of t, cosine of t, and 1. Now, there should be a prime here, by the way, right there. So the unit tangent vector is r prime of t divided by the length of r prime of t. So the length of r prime of t equals the square root of 2. So how are we getting that? Well, if you look at the length of r prime of t, that's the square root hold on. Okay, so that's the, so what I'm doing is I'm computing the length, and I'm sorry, I'm gonna do my writing well. Like things to be clear. Okay. So what I'm trying to do is I'm trying to justify this root 2 here, how we're getting it. Okay, so the length of the derivative vector is going to equal the square root of sine squared t plus cosine squared t plus 1. But what is sine squared of t plus cosine squared t equal to for any angle t? That's the Pythagorean identity, right? What's sine squared plus cosine squared equal to? That's right, Ian. That's right. It equals 1. So, hold on, did it get erased? What happened? Is my stuff still there, class? Are you seeing my writing, or did it get, all right. All right, we'll do it again. Come on, what's going on here? All right, thank you. All right, so again, square root of t, how am I getting that? That's the length. This is r prime, by the way, class. It should be an r prime there, right here. Okay, so let's, okay. Okay, and like you said, sine squared plus cosine squared of t equals 1. And so that's how you get square root of 2. How many found that helpful? Was that helpful to see that? Maybe give me a thumbs up if that was helpful. Okay, good, Ellie. Excellent, excellent. All right. Thank you, Noah. Excellent, excellent. And so now we get our tangent vector. Here is the tangent vector right here. And it's a unit tangent vector. So now what we want to do is we want to find the normal vector. Well, the normal vector is equal to the derivative of the tangent vector over the length of, I'm sorry, the normal vector is equal to the derivative of the tangent vector over the length of the derivative of the tangent vector. We know, by the way, that the normal vector is orthogonal or perpendicular to the tangent vector, because the normal vector is just a multiple of the derivative of the tangent vector. So the normal vector points in the same direction as the derivative of the tangent vector. But the derivative of the tangent vector is perpendicular. It's perpendicular. That's what this symbol here means, right? It's perpendicular. The derivative of the tangent vector, t prime, is perpendicular to the tangent vector, t. And that's because the length of that tangent vector equals 1. It's a constant for any value of t. And therefore, those vectors are orthogonal or perpendicular. Okay, so, okay, it's no big deal figuring out the derivative of the tangent vector, t. And let's see here, the length of the derivative of my tangent vector is equal to 1. Okay, thank you. And this will all be in the recording. Let me just see one thing on this. Hold on. I'm not sure I agree with this, what I have written down here. Hold on, I'm not sure I agree with this. One moment. One moment, class. What I'm trying to do, class, is I'm trying to, this root 1 here, this square root of 1, I'm trying to, what I got to do is I got to take this derivative of the unit tangent vector and show that its length equals 1. Okay, I got to show that its length equals 1. It should. I'm just, for some reason, I'm having trouble seeing it. Yeah, well, cosine squared plus sine squared equals 1. So let me try it here. Hold on. So let me put it in maybe in blue. Okay, so this is the length of this vector. Right? And the 1 over root 2 should come out. Right? The 1 over root 2 should come out. Then we have the square root hold on. Yeah, we have the square root of negative cosine of t squared plus negative sine of t squared plus 0 squared. And I'm getting 1, okay. That's 1 over root 2. Okay. So now that makes sense. Here's what I did. Here's what I should have here, class. Let's fix this right now. Up here, I should have 1 over root 2. And here. Yeah. Let's fix that right now. I like things to be clear, you know. I like them to be. So 1 over root 2 divided by 1 over root 2. That's what we're okay, and this whole thing, 1 over root 2 divided by 1 over root 2 is 1. Okay, so now that explains it. It was confusing for me there. Okay. Are there any questions on this? Square root should really go down a little more there. How many found this helpful? Was this helpful? This little. Okay, good, Ian. Good, Ellie. Okay, so, and actually, I'm going to get my notes. Let me just do that right now, so there's nothing to worry about. Okay, so now, at t equals pi over 2, I substitute t equals pi over 2. Thank you, Ian. Thank you, Ellie. In the normal vector and in the tangent vector, the t for the time t for the tangent vector and the normal vector, and that's what I'm doing here. And then when I do the cross product, okay, I can factor out that 1 over root 2, and I end up getting for the cross product vector between those tangent normal vectors at t equals pi over 2, I get 1 over root 2 times the vector 1, 0, 1. Okay. Much better, much better. All right, and when you're ready, I'll move to the next page. So this binormal vector, okay, it is the vector that is perpendicular to the plane containing those unit, tangent, and normal vectors. And so, and it turns out that the binormal vector itself has length 1. Let me show you why on the next page here. May I go to the next page? Who's ready? Maybe give me a thumbs up. Okay, excellent. Thank you, everybody. Okay, on to the next page. So why is the length of the binormal vector at pi over 2 equals 1? Well, remember how cross products defined. The cross product of the two vectors is equal to the product of the lengths of the two vectors times the sine of the angle between the two vectors. But the tangent vector is perpendicular to the normal vector, and so that angle between the two vectors is pi over 2. Well, the sine of pi over 2 is 1, and the tangent and normal vectors are unit vectors. They have each length 1, and so the cross product. I want to say it's the right way. I need to add this. I forgot. I'm doing right the length, right? So I need to include those symbols there. The length. So the length then is of that cross product vector, which is the binormal vector. I mean, this is the binormal vector, right? Its length does equal 1. And we just proved it. So it's nice to know. Now the book just says, oh, its length is 1. The binormal vector also has length 1. But they don't really, they don't like say why. Well, now you know why. So, okay, we want the equation of the oscillating plane. Okay, and of course, the 0, 1, and pi over 2 is the point on the point. Well, it's a point on the helix, but the oscillating plane kisses the helix, and it contains that point. So we have a point on our oscillating plane, and we know that the normal vector to the plane is the binormal vector. Well, the binormal vector remember what the binormal vector was from the previous page. The binormal vector at pi over 2 was equal to 1 over root 2. Hold on, it was equal to 1 over root 2 times the vector 1, 0, 1. But in terms of and that binormal vector is perpendicular to the oscillating plane. But direction is determined by these components 1, 0, 1. The 1 over root 2 here, doesn't affect the direction. So when I have my numbers here for the equation of the plane, the A, B, and C, I just really need the components of that perpendicular vector. And you work it out, the 1 over root 2 can be excluded. That scalar multiple. So z will equal negative x plus pi over 2. It's still the same example, Hyunu. We're still doing this example, and I know that you had your internet went off for a little bit. It's all going to be in the recording, which I'll upload to course content. Course content link in Blackboard. You're welcome. You're welcome. So in terms of a picture, I mean this is a two-dimensional picture. It's just showing how this oscillating plane cuts the xz plane. We know that oscillating plane goes on forever. This is just like a cut of it right here. Now the equation of the normal plane, of course, that's the plane. What vectors does the normal plane contain? Do you remember? You have the unit tangent, normal, and binormal vectors. The oscillating plane contains what two vectors? I'm sorry, the normal plane. The normal plane contains what two vectors? You have vector n. Charles, you are half right. The normal plane is going to contain the normal and binormal vectors. And that means what vector is perpendicular to the normal and binormal vectors? What vectors then perpendicular to those? The plane that contains the normal and binormal vectors, the unit tangent vector is perpendicular to the plane that contains the normal and binormal vectors. That's correct, Charles. And so that means then that to get the like the numbers here, I already know the point on the point on the normal plane is 0, 1, pi over 2. So I have my point on that normal plane. Now I need the A, B, and C for the equation of the plane, and I'm using -1, 0, 1. Now let me just go back for a minute. -1, 0, 1, if we note here, that if we do, let me put it in blue here. If we do r prime of pi over 2, that's negative sine of pi over 2, cosine of pi over 2, and 1. And that will equal -1, 0, and 1. So what I did was I used, instead of using the tangent vector, which would have, I'll say it, let me just say it the way I want to say it. The tangent vector at pi over 2 would be equal to 1 over root 2 times the vector -1, 0, and 1. Okay? But both of these vectors, r prime of pi over 2 or tangent of pi over 2, are acceptable for using the A, B, and C values for the equation of the normal plane. Because both of these vectors here are perpendicular to the normal plane. The unit tangent vector that has the only difference between r prime, the derivative of, r prime of pi over 2, that vector, and the tangent vector at pi over 2, the only difference is the tangent vector has 1 over square root of 2 as a scalar. But that doesn't affect the direction. So why not just use the derivative vector at pi over 2? Okay, and that's what I do. So I'm just trying to tell you where these numbers come from a little bit. And so we get then the equation of the normal plane. Z equals x. Z equals x plus pi over 2. And incidentally, if you look at the little picture here, hold on, do I have it? Hold on. If you look at this, oh, I guess it was on the same page. If you look at this picture, which is just a picture of how the planes cut the XZ plane, you can see the two planes are orthogonal. Okay, you can see that. Okay, so let me know if you have any questions, please. We still now have to get to the curvature. All right, are we ready? Are there any questions before we move on to the next page? Who's feeling good so far? Okay, good. Comfortable with the material. I met the Ellie's feeling okay. Juliana and Madeline are good. Okay. Well, let's now get to the curvature on the next page. So curvature for the helix, here's the definition of curvature. Okay, one of the, that's Formula 9 from page 710. Okay. And we know there are other ways to find curvature as well. But I'm just choosing to use this definition of curvature. And, you know, I feed in here's the derivative of my unit tangent vector here. Here's the derivative of my position vector there. Okay. And it's just really a matter of computing things out. I hope everything's pretty clear. Let me know if you have any questions up to here. You end up getting a half for the curvature. So we end up getting constant curvature for now, you know, what I'm doing is, in other words, the space curve, I mean, normally space curves, curvature varies as t varies. In other words, as t varies, the position vector that traces out the space curve, well, no, as t varies, the position vector traces out the space curve in space, and curvature is going to vary depending on what t is. It'll be a function of t. But in this case, for the helix, the curvature is constant. Does it make sense that the curvature would be constant for the helix based on what you know a helix looks like? Yeah, that makes sense. To E and it makes sense. Absolutely. Right? So a helix has constant curvature. Absolutely beautiful. Absolutely beautiful. Please let me know if you have any questions. All right, I'll stop the recording then.